Welcome to The Explainer. Today, we're diving headfirst into the incredibly fascinating world of cellular neuroscience. We're looking at some truly groundbreaking research that is completely flipping the script on how we understand neurodegenerative diseases. So, I've got a question to start us off. What do a Parkinson's movement drug and the memory of, say, a warm chocolate chip cookie have in common? I know, it sounds like a weird riddle, right? But the answer holds a massive plot twist in the story of Alzheimer's and Parkinson's. We are about to uncover a totally surprising overlap between these two devastating conditions, an overlap that could quite literally change everything about how we treat them. Here's our roadmap for today. First, the neurodegeneration puzzle. Then, Alzheimer's early energy crisis. Third, the dopamine memory twist, followed by reprogramming cells for Parkinson's, and finally, rebuilding the human brain. Okay, let's dive into this. Part 1. The neurodegeneration puzzle, the traditional view. For the longest time, the medical world put Alzheimer's and Parkinson's into totally separate boxes. They were viewed as completely distinct diseases with distinct symptoms driven by totally different chemical culprits. You've got Alzheimer's on one side, famous for memory loss and the physical buildup of amyloid plaques in the brain, and then Parkinson's on the other side, known for movement issues, tremors, and a severe loss of a chemical called dopamine. But recent research? It's completely cracking this rigid divide. The biological boundaries are actually blurring, and that is exactly where our first major plot twist begins. Which brings us to Part 2, Alzheimer's early energy crisis, the mitochondria connection. To really grasp this energy crisis, we need to zoom way in, down to the microscopic cellular level. Because Alzheimer's might not just start as a plaque problem. It might actually begin as a massive cellular energy failure. Think about it. Our brain cells rely heavily on mitochondria, the tiny power plants of the cell, just to function. And there's this crucial protein called MFN2, or mitofusin 2. You can think of MFN2 as the quality control inspector for these power plants. It actively regulates mitochondrial fusion, which is basically how damaged mitochondria repair themselves by fusing with healthy ones. This inspector keeps the whole cellular energy grid running smoothly. Now, what's really interesting about this timeline is how the disease actually unfolds. Researchers track this in a specific Alzheimer's model, the APKI mouse, which is a fantastic mirror for human disease progression. Look at what happens. At 3 months, there's mild amyloidosis. Those famous plaques are just starting to form. But the ATP, the actual cellular energy, is completely normal. But hit 6 to 7 months, and the mice start showing learning deficits. And right alongside that, a massive energy failure, driven by a severe drop in that MFN2 inspector protein we just talked about. All of this is happening way before the severe memory deficits and huge drops in oxygen consumption that don't show up until the 12 to 14-month mark. The power grid is failing early. Let's look at exactly what's going wrong at that crucial 7-month mark. The bioenergetic failures are honestly pretty stark. We are seeing decreased ATP production, meaning literally less fuel for the brain cells. At the same time, there's a higher mitochondrial membrane potential and way more reactive oxygen species, or ROS. Simply put, the power plants are working harder, but instead of making usable energy, they're just pumping out toxic exhaust. And the kicker right there at the bottom, a significant drop in MFN2. Because this quality control protein vanishes so early on, it suggests MFN2 could be an absolutely vital new therapeutic target. We might be able to fix the energy crisis before the brain gets severely damaged. Moving right along to Part 3, the dopamine memory twist, a Parkinson's chemical in Alzheimer's. If that energy crisis was twist number 1, this next discovery completely subverts almost everything we thought we knew about brain chemistry. I absolutely love this quote from Kei Igarashi at UCI Mind, who led this groundbreaking research. These experiments were like a detective story for us, and we are excited about the results. His team was basically hunting for a missing puzzle piece about how memories are made and lost, and what they found was completely unexpected. The whole mystery centered around something called associative memory. It's your brain's ability to link completely unrelated items. It's what allows you to connect a certain song to a first date, or the smell of a chocolate chip cookie, instantly bringing up a memory of your grandmother's house. The team discovered that this specific associative memory process is actually controlled by these highly specialized neurons called fan cells, which hang out in a part of the brain called the lateral entorhinal cortex. Now, here is where the paradigm completely shifts. Under the old way of thinking, dopamine was the movement chemical, right? Lose it and you get Parkinson's. But look at the new paradigm. researchers found out that dopamine actually controls those memory-forming fan cells. A deficiency in dopamine in this specific brain region is what drives memory impairment in Alzheimer's. It's wild. The researchers even gave Alzheimer's model mice levodopa, the standard go-to Parkinson's drug that boosts dopamine, and it actually improved their associative memory. Think about that. A Parkinson's drug fixing an Alzheimer's symptom. That is a staggering crossover. All right, part 4, a reprogramming cells for Parkinson's, the time machine. So if dopamine is really that crucial, what if we didn't just try to boost it with drugs? What if we could take the damaged brain circuitry of a Parkinson's patient and physically replace it to generate new dopamine? Welcome to autologous cell therapy. We are getting some mind-blowing clinical trial data from Aspen Neuroscience on this. It's a completely personalized treatment that uses a patient's own cells to replace damaged tissue. And because the cells are coming directly from the patient's own body, the massive leap forward here is that it requires absolutely zero immunosuppressant drugs. The body just doesn't reject its own material. Let's see how this builds into an actual functional process, a treatment called Succinate Pro-Cell Therapy. It's basically biological time travel. Step 1, doctors take a simple skin biopsy from the Parkinson's patient. Step 2, they literally wind back the biological clock, reprogramming those mature skin cells into what are called induced pluripotent stem cells, or iPSCs. Step 3, they coax those fresh stem cells into becoming brand new dopamine-producing precursor cells. And finally, step 4, those fresh cells are precisely transplanted right back into a region of the patient's brain called the putamen. It is literally turning back time on a cellular level. And this isn't just sci-fi theory. We have hard clinical proof backing it up. Looking at the 12-month data from Aspen's Phase 1/2a Aspiro trial, the results are incredibly promising. Patients in both the low and high-dose groups gained over 2 extra hours of good on time, meaning those crucial periods where their motor symptoms are well controlled. On top of that, their severe motor impairment scores dropped significantly. The therapy is actually working. These patients are getting real functional movement back. But the crucial point here is this specific number, 51.6. That is the percentage of mean improvement in quality of life scores for the low-dose cohort after a year, 51.6%. Patients are experiencing massive, tangible upgrades in their daily lives. Some are even able to lower their daily doses of traditional levodopa. And the medical scans? They prove the new grafted cells are surviving, locking into place, and successfully doing their job of rebuilding that broken neural circuitry. Finally, part 5. Rebuilding the human brain, the future of cellular repair. We've definitely covered a lot of ground today, but all these breakthroughs, they point to a unified, incredibly hopeful story about where the entire field of neuroscience is heading. Just to tie it all together, first, we're learning that neurodegeneration starts with micro-level failures, like a breakdown in metabolic energy and losing that MFN2 protein. If we understand that, we can target the power grid before the brain really declines. Second, we're cross-pollinating treatments. We're finding out dopamine isn't a one-trick pony for movement, and we might actually use Parkinson's drugs to treat Alzheimer's memory loss. And third, we are moving way past just managing symptoms. We're using cellular reprogramming and autologous therapies to physically rebuild damaged networks using a patient's own rejuvenated cells. Which leads us perfectly to one final provocative question. What if the future of treating brain diseases isn't just about managing the decline, but physically rebuilding our neural networks from the ground up? The science we just walked through today tells us that future isn't decades away. It's already arriving. Understanding these cellular plot twists means we don't have to look at these terrifying diseases as inevitable endpoints anymore. They're mechanical failures, and mechanical failures can be fixed. Thanks so much for joining me for this explainer. Keep learning, keep questioning, and I'll catch you next time.